All right, in this section, we're going to be taking dilations and putting them on the coordinate plane. But before we do that, let's just recall how dilations work from the first lesson. So we have a couple of primary properties that we finished up the last lesson with. When we do a dilation, there's always going to be a scale factor, and that scale factor is usually denoted with the letter K. It is going to be greater than 1 if we have an enlargement. So if we multiply the original figure by a number bigger than 1, then our resulting figure is bigger. And if it's between 0 and 1, the scale factor is between 0 and 1, then we'll be multiplying by a smaller number and shrinking the object. So the scale factor gets applied first, and also any image that's created will be parallel to the original. So those are the two main properties of dilations. We also had the notation, capital D for the function name, lower subscript C for the center point, whatever the center point may be, and an input and an output. All right, so with all that in mind, if we're doing a dilation on a coordinate plane, then what we want to do is take the points and apply the scale factor from the center. So this one is saying that these 3 points are plotted, and we're trying to find their images, dilation by a factor of 2, and centered at the origin. Now both of those things are important there because we have to know how far to go and from where. So to do this, we will figure out how far it is from the center point O to point A, and just double that distance. We'll keep it along the same path. Remember, dilations always travel along the same path. So to find A prime, we want to go twice as far from O as point A was. Point A was clearly 2 units away from O, and so if I go 4 units away, I'll find A prime. All right, and then point B is 4 units to the left. So to find B prime, I need to go 8 units to the left. And that point is actually misplaced. It should be here at -8, so you want to fix that on yours. B prime, it's listed correctly over here in the coordinate, but on the grid, it's in the wrong spot, so it should be at -80. And so the last one, to get to point C, this is a little bit different because it's not a horizontal or vertical path. So to get to point C, it's up 4 units and over 3. So if you just use the slope, you think of it like a slope triangle here. Then to get to C prime, we just need to apply the very same slope triangle to get twice as far away. So instead of counting units, we count slope triangles essentially. It's a 4 by 3 and another 4 by 3. And we end up at C prime that way. So finding the dilation on a grid is simply doubling the distance if the scale factor is 2. Whatever the scale factor may be, we use the grid marks. So how can we verify that C prime is twice the distance away? Well, we can use distance formula. And if I have a 4 by 3, it's 4 squared plus 3 squared. If I have it turns into an 8 by 6 triangle, the big triangle from O to C prime, that would be 8 squared plus 6 squared. And it comes out to 5 and 10 when we do the distance formula. So we can prove it that way. Dilations from the origin are the most important in the coordinate plane. It's typically where they come from. So to explain how they work from an origin with a rule set up, if we have any point in the plane xy, then after dilating, whatever the scale factor will be, the coordinates are going to be that scale factor times x and that scale factor times y. So coming from the origin, that 3, 4 turns into 6, 8. So even without a slope triangle, we can calculate the coordinate just by applying the scale factor. Gets a little bit different if the center of dilation is not the origin, and we'll see an example of that later. All right, example 2. Which of the following is the image of -4, 10 after a reflection in y equals x and then a dilation from the origin with scale factor 3/2. So we have to go in order. If we reflect over y equals x, this goes back to a previous unit. We're just going to switch the coordinates. Y literally equals x, and so 10, -4 is the result. We don't need a grid for that. We just know that they're going to switch. And then once we're at 10, -4, to dilate, remember we just apply the scale factor. So multiply by 3/2 on both of them, we end up with 15 and with -6. Again, that's because it's coming from the origin. When it comes from the origin, the scale factor can simply be multiplied. All right, so that's exercise 2. Exercise 3, we've got segment AB already drawn. We have -1, 4 and 4, 2. So we want to try to plot the image of that segment after dilating by 3 from the origin. So what we can do is just multiply the coordinates by 3. So A turns into A prime by multiplying by 3, -3 and +12. Same thing with B, becomes 12 and 6. If we plot those 2 points and connect them, we get segment A prime, B prime. Now that segment is parallel to the original one. That's what part B is talking about here. If you just check the slopes, you can see that they're parallel. This one, AB, is down 2 units and to the right 5, and A prime B prime is down 6 units and to the right 15, which reduces to negative 2/5. So the segments are in fact parallel. And to check the distances, what should happen before we actually check the distances, it should be 3 times as long, because the scale factor should dictate how the new segment relates to the original. So as we check these distances, that's what we're hoping for. So to get from A to B, if we just take this original segment, it's a 2 by 5 triangle, so 2 squared plus 5 squared. That's going to give us root 29, and the distance formula has been applied here. And to get from A prime to B prime, it's going to be 6 and 15, so 6 squared plus 15 squared, and that's root 261, which divides by 9. And so if you rewrite that radical, the simplified form would be 3 root 29. And so you can see that that is in fact 3 times the original distance. So by putting it in simplest radical form, it's very easy to tell that that scale factor has been applied. If you just typed it into your calculator, root 29 and root 261, and checked those versions, the decimal versions, you could also see that that's 3 times. But simplifying the root just shows it real clearly that we've tripled the distance. Okay, so we can verify those using those coordinates that it does 2 things. It maps parallel segments and gets the correct scaled length. All right, exercise 4. So a line whose equation is 3y plus 5x equals 12, dilated at the center, scale factor of 1/2. So what that tells us is the new line should be parallel, because all dilations move in a parallel fashion, and any coordinates should be half as far away from the origin as the original ones. So if we look at this equation in graphing form, solving for y, subtract the 5x, divide by 3, negative 5/3 x plus 4, one thing we know about that equation is that it has a slope of negative 5/3. And so therefore, any dilation equation should also have a slope of negative 5/3 because it's parallel. The second thing we know is that it has a y-intercept of 4. So if we're applying a scale factor of 1/2, that point, that y-intercept is one of the points on the line. So that point should be half as far from the origin as it originally was. So if the original y-intercept is 4, the new y-intercept will be 2. And we'll go over in class how to do this with point-slope form too, but slope-intercept form would say maintain the slope and apply the scale factor to the y-intercept. And that's how you'd get a new line that's parallel and half the distance from the origin. And exercise 5, explain why dilating the line y equals 3x by a scale factor of 2 would not change the equation. Well, think about this. There's two components to it, right? So we have a slope, we have and we also have a point. Well, the slope is going to be maintained. It's still going to be 3. And so the y-intercept in this case is 0, 0, 0. So if I dilate 0, 0 by 2, it's still 0, 0. So because that point falls on the origin, I can't bring it in toward the origin or out away from the origin. It's just going to stay there. And so it's going to have to be the same line. So in this diagram you see here, segment AB, which has point C on it, it's still going to be the same line. If I dilate out to A prime and out to B prime, it's still exactly the same line. It hasn't changed. It's just gotten longer, sort of, but it was infinite to begin with, so it didn't even really get longer. Just the points on the line got farther away.